What is the main motivation behind the proposed Selective Language Modeling (SLM) approach?
The main motivation behind the proposed Selective Language Modeling (SLM) approach is to enhance the efficiency and performance of language models during pre-training by selectively focusing on tokens that exhibit high excess loss compared to a reference model. The goal is to improve the quality of training data by filtering out noisy and irrelevant tokens, while prioritizing tokens that align better with the desired distribution for downstream applications. By training the language model only on tokens with high excess loss, SLM aims to optimize the learning process, stabilize the model's training trajectory, and enhance its overall efficiency. This approach allows for the identification and prioritization of tokens that are most beneficial for the model's performance on specific tasks, leading to improved perplexity scores and performance on downstream benchmarks.
How does the Selective Language Modeling (SLM) approach differ from traditional causal language modeling (CLM)?
The Selective Language Modeling (SLM) approach differs from traditional causal language modeling (CLM) in that SLM focuses on training the language model selectively on tokens that exhibit a high excess loss compared to a reference model, while CLM employs cross-entropy loss on all tokens in the sequence. SLM uses a token selection ratio to determine the proportion of tokens to include based on their excess loss, ensuring that only the most beneficial tokens are trained on. In contrast, CLM applies the loss function to all tokens in the sequence uniformly. SLM introduces a novel approach where a reference model is used to score tokens and selectively train the language model on tokens with high excess loss, aiming to improve efficiency and performance by excluding irrelevant or low-quality tokens. On the other hand, CLM does not incorporate a reference model for token selection and trains the model on all tokens in the sequence without prioritizing specific tokens based on their loss.
Can you explain the process of token selection in the SLM approach?
The process of token selection in the Selective Language Modeling (SLM) approach involves three main steps. Firstly, a reference model is trained on a high-quality dataset to establish a baseline for token evaluation. This reference model computes the loss of each token in the pre-training corpus based on the probability it assigns to the token. Tokens with high excess loss compared to the reference model are considered more learnable and aligned with the desired distribution. Secondly, tokens with high excess loss are selectively chosen for training the language model, focusing on those that are most beneficial for downstream applications. The excess loss for each token is calculated as the difference between the current training model loss and the reference loss. A token selection ratio is introduced to determine the proportion of tokens to be included based on their excess loss. Finally, the language model is trained only on the selected tokens using the cross-entropy loss function, which ensures that the loss is applied only to the tokens deemed most beneficial for learning. This process efficiently excludes irrelevant or low-quality tokens without additional costs during pre-training, enhancing the model's efficiency and performance on downstream tasks.
What is the significance of the reference model in the SLM approach?
The significance of the reference model in the Selective Language Modeling (SLM) approach is crucial for token-level data selection during pre-training. The reference model is trained on a curated high-quality dataset to establish a baseline for assessing token loss within a larger pre-training corpus. By evaluating the loss of each token based on the probability assigned by the reference model, the SLM approach can identify tokens with high excess loss compared to the reference model. These tokens are considered more learnable and aligned with the desired distribution, leading to their selective inclusion in the training process. This selective approach allows the model to focus on tokens that are most beneficial for downstream applications, excluding irrelevant or low-quality tokens. Ultimately, the reference model serves as a guiding mechanism for token selection, enhancing the efficiency and performance of language models during pre-training.
How does the SLM approach improve token efficiency during pre-training according to the paper?
The SLM approach improves token efficiency during pre-training by selectively focusing on tokens with high excess loss between the training model and the reference model. This method involves training a reference model on a high-quality dataset to score tokens based on the desired distribution, filtering out irrelevant or low-quality tokens. By training the language model only on tokens with high excess loss, the SLM approach ensures that the model learns the most beneficial tokens for downstream applications. This selective training process enhances the model's ability to focus on tokens that align with the target distribution, leading to improved performance and efficiency during pre-training. The SLM approach effectively identifies and prioritizes tokens that contribute the most to the model's learning process, resulting in enhanced token efficiency and overall model performance.
What are the key findings regarding the effectiveness of SLM on math continual pre-training, as mentioned in the paper?
The key findings regarding the effectiveness of Selective Language Modeling, SLM, on math continual pre-training, as mentioned in the paper, include the following. 1. SLM outperforms CLM, trained baselines by over 16% on the GSM-8K and math datasets. 2. RHO-1 to 7B matches the state-of-the-art performance of DeepSeek Math 7B using only 15B tokens, compared to the 500B tokens required by DeepSeek Math. 3. RHO-1-1B achieves 46% accuracy on the math dataset, becoming the first 1B LM to exceed 40% accuracy, nearing the early GPT-4's COT performance of 42.5%. 4. SLM reaches baseline accuracy up to 10x faster, demonstrating its efficiency in training language models. 5. SLM significantly enhances token efficiency during pre-training and improves performance on downstream tasks. 6. RHO-1 models trained with SLM show improved perplexity scores on benchmarks for models trained with selected tokens. 7. RHO-1 demonstrates a certain degree of generalizability on unseen tasks, with an average few-shot accuracy improvement of 6.2% on RHO-1 Math 1B and 2.7% on RHO-1 Math 7B. 8. RHO-1-1B and RHO-1 7B achieve a state-of-the-art 46% and 51.8% accuracy on the math dataset, respectively, when fine-tuned. 9. SLM effectively identifies tokens relevant to the target distribution, resulting in improved performance on downstream tasks. 10. The selected tokens by SLM align better with downstream performance, showing a positive correlation with the performance of downstream tasks, indicating the efficiency of token selection in pre-training.
How does the paper demonstrate the efficiency of RHO-1 models compared to other baselines in terms of accuracy and token usage?
The paper demonstrates the efficiency of RHO-1 models compared to other baselines in terms of accuracy and token usage by introducing Selective Language Modeling, SLM, as a method to improve language model training. The SLM approach selectively removes the loss of undesired tokens during pre-training, focusing only on tokens with high excess loss between the reference and training model. This selective training results in significant improvements in accuracy and token efficiency. The experiments show that RHO-1 models outperform CLM trained baselines by over 16% on the GSM-8K and math datasets. RHO-1 models achieve baseline accuracy up to 10 times faster and match state-of-the-art performance with significantly fewer tokens compared to other models. For example, RHO-1 7B matches the performance of DeepSeek Math 7B using only 15B tokens, while DeepSeek Math required 500B tokens. Additionally, RHO-1-1B becomes the first 1B LM to exceed 40% accuracy, nearing the performance of early GPT-4's COT. The paper's findings indicate that SLM effectively identifies tokens relevant to the target distribution, resulting in improved perplexity scores on benchmarks for models trained with the selected tokens. Overall, The results demonstrate that the SLM approach significantly enhances token efficiency during pre-training and improves performance on downstream tasks, showcasing the efficiency and effectiveness of RHO-1 models compared to other baselines in terms of accuracy and token usage.
What is the impact of the token selection ratio on the SLM approach as discussed in the paper?
The impact of the token selection ratio on the Selective Language Modeling (SLM) approach is crucial in optimizing the efficiency and effectiveness of pre-training language models. The paper discusses using a token selection ratio, such as 60% for the TINYLLAMA1, 1B model and 70% for the Mistral 7B model, to determine the proportion of tokens included based on their excess loss compared to the reference model. By selecting tokens with high excess loss, the SLM approach focuses on those that are more learnable and aligned with the desired distribution, excluding irrelevant or low-quality tokens. The token selection ratio directly influences the quality of tokens chosen for training, ensuring that the model learns from the most beneficial tokens while excluding noisy or irrelevant ones. This strategic token selection process enhances the model's training efficiency and performance on downstream tasks, as demonstrated in the experiments conducted in the paper.
How does the paper analyze the tokens selected by the SLM method during pre-training?
The paper analyzes the tokens selected by the Selective Language Modeling (SLM) method during pre-training by visualizing the token selection process and evaluating the perplexity of these tokens at different checkpoints. The analysis involves highlighting the tokens retained during actual pre-training, with a focus on tokens closely related to mathematics, indicating effective training on relevant content. The study also examines the differences in token filtering across various checkpoints, showing that tokens selected by later checkpoints tend to have higher perplexity towards the later stages of training and lower perplexity in the earlier stages. This suggests that the model optimizes tokens with a larger learnable space first, enhancing learning efficiency. Additionally, the paper observes a double descent pattern in the loss of selected tokens, where perplexity initially increases before decreasing, potentially due to selecting tokens based on excess loss to target those most in need at each checkpoint.
What insights does the paper provide on the relationship between selected token loss and downstream task performance?
The paper provides insights on the relationship between selected token loss and downstream task performance by demonstrating that selecting tokens for pre-training based on their excess loss compared to a reference model can significantly improve the model's efficiency and performance on downstream tasks. The Selective Language Modeling (SLM) approach focuses on training the language model selectively on tokens with high excess loss, which are deemed more learnable and aligned with the desired distribution. The study shows that training on selected tokens leads to a more significant decrease in downstream loss compared to training on all tokens. This is illustrated by the positive correlation between the average loss of selected tokens and the performance of downstream tasks, while the average loss of unselected tokens exhibits a negative correlation with task performance. By targeting tokens with high excess loss, SLM optimizes the learning process, enhances model efficiency, and improves performance on downstream tasks.